Hi, welcome back to this course on computational thermodynamics and kinetics of materials. In this class, we will deviate from ternary to binary, discuss something more on phase transformations in binaries, especially the reactions and some other types of phase transformations. Then we will again go back to ternary and see something called ternary projections, especially liquidus projection. When we say reactions, we said this horizontal line will be there. It's a pattern of a reaction in a phase diagram. This horizontal line is a pattern of a reaction in a binary phase diagram. So this one particular reaction we have already seen, eutectic reaction, where liquid gives two solids. An example is in a silver copper system. There are other types of reactions, for example, peritectic reaction. This is one more type where liquid plus a solid gives another solid. You can see here, this is the pattern for it. One side liquid, one side solid. The sides can be switched. Liquid can come here, solid one can come here. Doesn't matter. At one side we have liquid and one side we have solid. These two things combine to give a new solid. So for example, in gold iron system, we see this kind of a transformation. The third type is monotectic reaction, where a liquid gives another liquid plus a solid. So this is how its pattern will look in the phase diagram. A solid here, a liquid here, and another liquid here. What happens is this liquid is undergoing the reaction and it becomes a solid and another liquid. Okay, and there will be this kind of a pattern in monotectic reaction. Right. Then eutectoid reaction. In this case, there is no liquid. Parent or product, if you see, there is no liquid involved here, but it looks very similar to the eutectic. But in the eutectic, liquid gives two solids. Here, one solid gives two other solids. Okay, so solid 1 gives solid 2 and solid 3. Example is iron moly system. In peritectoid reaction, which is similar to peritectic but without the liquid on one side. So it is one solid and another solid combined to give a third solid. Product is a new solid here. Okay. So niobium hydrogen system has this. Then monotectoid reaction, it looks similar to monotectic except that there is no liquid here. Both the things here are solids. So one solid gives two solids. Okay, so this may look similar to this eutectoid reaction, right? So here one solid gives two solids, here also one solid gives two solids. But the distinction between eutectoid reaction and monotectoid reaction is the two solids that are there here. The one is S1 is the parent and S2 is a product. Okay, S1 and S2 will have the same crystal structure. Their chemical compositions will be different as indicated by this point and this point, but their crystal structures will be different, will be same. Whereas in this case, the crystal structures need not be same. This is one more type, syntectic reaction. Liquid 1 plus liquid 2 gives a solid. Two liquids combined to give a solid. In potassium zinc system, we see this. So these are some types of reactions. This congruent melting or freezing is not a reaction, but it has this kind of signature where liquid transformed to solid. Essentially, if liquid is cooled crossing this line, without any change in the composition of liquid, it entirely becomes solid. Okay. Usually, if you see any liquid crossing the solidus line, any liquid crossing the liquidus line, it will create transform to a small amount of solid with entirely different composition. But in this case, liquid transforms to a solid of same composition fully. Okay, that is one. That is called congruent melting. ALNI system is an example for that. Then there are things called order-disorder transformations, where a phase without any chemical order at high temperature becomes chemically ordered below a certain temperature. Okay, so this beta becoming beta prime is order to disorder transformation. Low temperature phase will be usually ordered. So example is copper zinc system. So now that we have looked at different reactions and transformations, let's take a binary phase diagram and try to identify these patterns so that we are familiar with these reactions. That would be a good exercise to do. Okay, so one side we have aluminum here, the other side nickel, and there are many horizontal lines and many intermetallic phases in AlNi system. We have seen this phase diagram before. How to identify the reactions? First reaction is there is a eutectic reaction. Liquid is becoming two solids. So this is the kind of pattern we said for eutectic reaction. That this is going to be slightly different, and this is actually happening here. But identifying that would not be that straightforward because the exact pattern will not be there. It is slightly skewed. It may look like this: liquid giving aluminum solid solution and Al3Na2. So this V here is going to look like this. So this is a slightly skewed V, right? So this is where the liquid phase will be, and on one side we have solid 1, which will be aluminum solid solution. It barely has any solubility to nickel, so it's not going to have a small range like V kind of thing here. It's going to look like a straight line in a typical phase diagram. And on the other side we are going to have a solid 2, which is going to be a line compound Al3Ni. So it's also going to look like a straight line. So you can transfer this here and see here, this is where it is. So liquid becoming one aluminum rich solid solution and Al3Na on this side. So this is the pattern, we can recognize that. So this is an eutectic reaction. That is one reaction. Then we have peritectic reactions. One peritectic reaction is here. The reactants and products are slightly different. Liquid is liquid plus one solid, AlNi is the solid. These two combine to give a new solid Al3Na2. And this is how it looks. The liquid in the conventional pattern that we saw, we have put it in the right side. It's going to be in this case in the left side, AlNi is on the right side. So these two things combine to give a new solid Al3Na2. The product here below this V sort of thing is here. So this is that V now, okay, Al3Na2. Okay. It's a very narrow ranged compound, and you can see this is here. Okay, so this Al3Na2 is the product. AlNa is the one solid which combines with this liquid to give this new solid Al3Na2. So that is the pattern, right? So that is one peritectic reaction. There is one more peritectic reaction here. Let's see what is that. So it is this liquid plus Al3Na2. This is the first solid. These two things combine to give a new solid Al3Na. Okay, so this is how the pattern is. The product is a line compound now. So there is no V sort of thing here. It's just a straight line. So Al3Na is the product. So this pattern is here. You can see there is liquid on one side. This liquid combines with the solid on this side, which is Al3Na2, giving this new product Al3Na. So it may be slightly difficult at this point in time. If you keep trying to recognize patterns like this, it will become easier. So that is another peritectic reaction. There is a peritectoid reaction here. Solid 1 plus solid 2 gives new solid. That is peritectoid reaction. This is the pattern we saw. And here it is here. But the reactant and products are going to be different. AlNi plus Na3Al. These are the two solids. Combine give the new solid Al3Na5. Okay, this is how the reaction is. AlNi on one side, Na3Al on the other side. These two solids combine to give the new solid Al3Na. This is where the pattern is. You can see here. This side it is Na3Al. This side it is AlNi. These two things combine to give the new solid Al3Na5. Then there is a congruent melting here. This is not a reaction. This is a congruent melting. It's happening here. The liquid is transforming to a solid, which is the compound AlNi, the intermetallic phase AlNi. Okay, so liquid is transforming to AlNi like this. So this pattern is here. So liquid, if it crosses this line, without change in composition, the entire liquid becomes AlNi phase. Okay, so that is the congruent melting. Then what about this region here? It is slightly tricky. Let us zoom it. We can see it clearly now. There are more things. So one side we have a eutectic reaction, liquid giving two solids. The pattern is here. Liquid gives one solid AlNi plus the other solid Na3Al. So you can see it here. Okay, the V is here. This is the liquid transforming to the first solid Na3Al this side and the other solid AlNa this side. So these two solids form from liquid. Then here we have a peritectic reaction, this horizontal line. What is that? A liquid plus a solid, nickel-rich solid solution combined to give a intermetallic phase Na3Al. It is here. I hope you could recognize this. So yeah, you can take any random binary phase diagram and try to recognize what reactions are there. If the moment you see a horizontal line, you should latch on and see what is the kind of pattern there. Now test your understanding with this. Identify the reactions, reaction temperature, involved phases, parent and product phases in a reaction, compositions of phases in AlZr phase diagram. So this is a AlZr phase diagram given here, multiple intermetallic phases. All these red color lines, horizontal lines here, they are all reactions. Okay, so take your time, try to identify them. 1 or 2 points may be slightly tricky, but most of them will be straightforward. Try to see that. Pause and try it yourself. So now I will play the answers. Now this part in the left extreme, this is where we start. This is the first reaction we see from left to right. That reaction, if I slightly zoom in, we can see it clearly. Perhaps if you have not gotten it first time because of this problem here, that's okay. Other reactions I hope you would have got. So this is here liquid plus this region is labeled as liquid plus Al3Zr for clarity. But if you see this horizontal line is here. On one side we have FCC in this bottom. On the other side it's Al3Zr. So looks like this FCC is actually starting here. If we zoom in, we can see it is actually starting from here. Okay, and the left extreme we see the liquid phase. So liquid plus Al3Zr on this side, they two combine. That's why this region is labeled as liquid plus a solid. This is a two-phase region. Okay, so these two things combine to give FCC. Okay, so this is the pattern here. Liquid plus solid gives a new solid FCC. So the liquid is here and the solid is here. They combine to give a new solid here FCC. So that region is quite tricky to visualize without zooming in. Now we have done that. This reaction here in the top. So this is the second reaction where we see a V sort of thing. So this is liquid giving one solid Al3Zr and the other solid Laves phase. So liquid giving two solids is eutectic reaction, that is this. The third horizontal line that we see is a peritectic reaction. Liquid on one side, solid one on one other side. So Laves phase and liquid. They two combine, give this line compound. This is the new solid that is forming in the peritectic reaction. The new solid is Al3Zr2, right? Then we have this one more horizontal line coming. This is a eutectic reaction. There is a V here. So liquid is there in the top. It is becoming two solids. One Al3Zr2 on this side, the other Al4Zr5 on this side. Okay, so you can see this Al3Zr2 is forming by peritectic reaction in these composition ranges. Okay, for this is also two-phase region. Okay, if you see Al3Zr2, this is this line compound. Laves phase is here. So this is a two-phase region with Laves phase and Al3Zr2. Similarly, to the right of this line, we will have Al3Zr2 and Al4Zr5 two-phase region. Okay, in both these regions, Al3Zr2 is present. But for these overall compositions before this line, they might have formed due to this peritectic reaction. But overall compositions after this line, they might have this phase will form through this eutectic reaction. Okay, then there is one more line here. This is again peritectic. Liquid plus Al4Zr5, one solid and one liquid combined to give a new solid Al2Zr5. And then we have this tricky region. We'll let us bring it zoomed in version like this. So this is this particular region. You can see x-axis It's here 60 to 76%, y-axis 1320 to about 1400. Okay, so we have really zoomed into this temperature range and this composition range here. That's what this is. You can see there is a peritectic reaction, liquid plus one solid Al2Zr3 combined to give a new solid Al3Zr5, that is here. And this horizontal line here is liquid giving one solid Al3Zr5 this side and BCC this side. Okay, so that there is one peritectic and eutectic reaction in this zone. There are two red lines which are very close. That's what they mean. Then there is another line here which is only between solids. There is a BCC solid on this side. There is this vertical line which is Al3Zr5, that is on this side. They two combine to form this new solid AlZr2. So two solids combine to form a new solid. What is that kind of reaction? It's peritectoid reaction. Okay, so that is happening here. And there is a red line here. This is one solid Al3Zr5 becoming two solids. Okay, so Al2Zr5 and AlZr2. One solid becoming two solids is eutectoid reaction. Okay, so there is a horizontal line here. This is BCC on this side, AlZr2 on the other side. They two combine to give this V here. Below the V, we have this HCP. Right? So this is two solids combining to give a new solid, which is again peritectoid. Okay? So this is how you recognize the reactions in this. So I hope you are getting familiarized with this exercise. So that is about the reactions in the binary. Now this is a good time to learn about ternary projections. This is going to be a 3-component system. A 2-dimensional diagram we are going to make, that is going to be the projection. So it's going to look like the Gibbs triangle. Within that, what we are going to have is not simply the phase stability regions. We are going to have something different that is called as a liquidus projection. We are going to project liquidus lines in certain way in a 2-dimensional picture. That's what we are going to do. Our first example is going to be with this simplest of the ternary systems, where all the 3 sides we have isomorphous binary systems. Okay, so what is a liquidus projection and what is the use of it? We will see that. What is liquidus projection? You bring this liquidus surface first. So in a binary we say liquidus line. In a ternary we are going to have a liquidus surface. Above this surface everything is going to be liquid. Any composition you select, above this surface it's going to be liquid. Now take this liquidus surface, okay, and bring an isothermal section like this. It's one single temperature blade sort of thing. If you cut the liquidus surface with that, you can see they intersect over a line. Okay, this line over which the surface and this isothermal section plane are going to intersect. So this entire line has one single temperature. Okay, so this is a contour of one single temperature in liquidus surface. And we know before this line, whereas the compositions before this would have started to form solid, the compositions below this, these compositions would not have started to form solid, they will be still liquid. So that is what this contour line means. And if we do this at multiple temperatures and get these contour lines and project them into a 2-dimension, that's what a liquidus surface, that's what a liquidus projection is. So to summarize what we have done, find liquidus surface, cut it with an isothermal plane, obtain isothermal contour line as the intersection of the liquidus surface and the isothermal plane, then repeat at multiple temperatures. Let's say all those temperatures are very close by, covering this entire liquid to solid region. Then project the contour lines to a Gibbs triangle. So the view from top of the prism, if you view it from the top, the entire prism, and see these lines, how will they look? Okay. For example, if you look at this kind of Vietnamese rice fields, where you have a mountain and there are different cuts done at different altitudes and forming is done. And if you look at the entire thing from the top, they'll be looking like just lines in a plane. They'll be looking like just lines, just curves in a plane, right? So that's what we are talking about. So let's see how is it done. This is a small animation where you see again similar isothermal sections on all the sides, that kind of a ternary prism, and you see how the liquidus projection is identified from this. So these are all the cut surfaces at different temperatures, from high temperature to low temperature. The contour line, you can see this is the entire contour line. And if these things are taken and projected into a Gibbs triangle of this sort ABC, so they're going to look like this. So this is what a liquidus projection is. So I hope it is easy for you to visualize now. What if all the three sides we have eutectic diagrams like this? Okay, so all the three sides eutectic. There is no solubility for A in C or C in A. It's a system with almost no solubility for in the. It's a system with almost no solubility in solid state. Okay, so you can see at different temperatures how the contour lines look in the ternary prism, and there is a eutectic point here. It's getting it's going into the ternary regime like this, and there is a binary eutectic point. These are all binary eutectic points. They all go into the ternary like this, and they meet at a point which is called as ternary eutectic. So this is how all three sides eutectic will work, and when it is projected into the triangle below, this is how you see that all these contour lines you can see nicely temperatures are marked here, and you can see the region which is C plus liquid is here, and A plus liquid here is here, and B plus liquid is here, this entire region. So this sort of marking can also be done sometimes. And these lines, more importantly, are the eutectic lines. You see this curve which is going from here down towards the center kind of thing. This thing, if you see from the top, is going to look like a line like this. Okay, and they all meet at point E, which is the ternary eutectic point. Ternary eutectic point means that liquid gets converted to three solids, not two solids. That's ternary eutectic for you. So this is how the eutectic reactions will look in the ternary regime. Let's take an example of silver copper tin system. Silver copper tin is a quite important system where the solders, you see, solders usually are lead tin alloys, soldering alloys, and lead is toxic. So the lead free solders contain these two elements, silver and copper. So this is one so these are the binaries of this: silver copper, silver tin, and copper tin. So you can see the binary phase diagrams. All of them have a eutectic reaction in that. So silver copper is easy to see. In silver tin, there is a eutectic reaction here as a V sort of thing, liquid giving two solids, Ag3SN on one side and almost pure tin on the other side. Tin has very less solubility for silver. And here copper tin, again there is a similar reaction here, a tin rich solution and Cu 1.25 tin, compound of this stoichiometry. These two solids form from the liquid. There is a eutectic reaction here. Yeah, of course there are more reactions like this. So this is if you want to practice, you can try to identify these reactions. Let us, if these three go into a ternary system, these are going to be the sides of the ternary, and how the liquidus projection will look in that. It's going to look like this, quite complex. And the lines here indicate that the reactions follow these paths. You remember in the previous case, three eutectic reactions, they converge into one ternary eutectic. It's similar to that. If I zoom into that version, you can see it here. So there is a these two binary eutectics, and there is one more binary eutectic coming like this. They all meet here. So this is the ternary eutectic now. Okay. So how is this liquidus projection useful? If we take one overall composition here, let's say a tin rich composition, that's how the solder composition will be, and see what happens in that. Okay, let's try that. Okay. So two binaries are given here, silver tin and copper tin, just to make sure that, just for you to refer what kind of eutectic reaction is there in this. Okay, and here we are having this point X, which is the overall composition. So in this, we are going to see predicting the solidification behavior of lead-free solder. So this is going to be a tin-rich alloy. The composition is marked here. So the tin-rich corner of the diagram is given here. So this side it is copper in this extreme end, and in this extreme end it's going to be silver. So here we are having tin content mentioned in the axis here. So the diagram above shows the liquidus projection for the tin-rich corner of the tin-silver-copper system. The bulk composition of X. So this is the bulk composition marked as X, 3.77 atomic percentage of silver and 0.93 atomic percentage of copper, predominantly tin. It is plotted in red circle here, right? So what happens as this alloy solidifies? So this is the liquidus projection. As we said, the alloy lies in the tin plus liquid phase field. Okay, so this information is because the first solid to form tin is indicated here, because in this case tin has barely any solubility for the other two elements. So we can draw a tie line like this. As copper and silver are very insoluble in tin, less than 0.05% maximum solubility. Due to this, the solid phase can be assumed to be pure tin. That's the reason why we are drawing the tie line also confidently, because it's a liquidus projection. We can't draw a tie line in this that easily. So in this case, it is possible to draw. Okay, can be drawn from tin through the bulk composition. So through this point, we are drawing the line. So what does that line give us? It gives us how much is the solid and liquid present. As tin forms, the composition of the liquid moves away from the bulk composition along the tie line until it reaches the eutectic valley, shown by the blue circle. So this is the composition of liquid, meaning some solid has formed. Therefore, the composition of liquid will have whatever went into solid tin, it will be less in that liquid, right? So the composition of liquid will have less amount of the element which has gone into solid. So tin has gone into solid. So this composition will have, or liquid will have less amount of tin. At this point, the system has 2.1 atomic percent solid, which can be directly calculated by applying the lever rule here, this small length by the total length. So then we can see that the solid composition keeps changing like this, and the liquid composition moves along this line. Okay, what is this? The solid composition moving along this line is nothing but the eutectic reaction in the tin aluminum side, tin silver side is happening, and for each of this composition, whatever will be the eutectic product that will form, that is the solid. So the average composition of both the eutectic solid phases, eutectic product, is given by these dots. So that's why solid composition is moving like this, and the liquid composition moves down the eutectic valley, enriching in copper. So whatever solid forms is going to be rich in tin and silver only. So the liquid gets enriched in copper, eventually traveling along this eutectic valley, moving to this eutectic composition. Okay, so the composition of liquid moves down the temperature along the eutectic valley, shown by the blue circle. The solid enriches in silver, as shown by the green circle. The compositions are given by a series of tie lines. Okay, right. So the liquid eventually reaches the eutectic composition here. What does that mean? It's a ternary eutectic point, right? So there should not be any more liquid present after reaching this. So at this point, the system is 44.2 atomic percent solid. The bulk composition of the solid, 3.66 atomic percentage of silver, balance is tin. Okay, is given by the one end of the red line marked with the green circle. So that's going to be our solid. This corresponds to 4.9 atomic percentage of Ag3Sn, okay, which with the rest being pure tin. Okay, so that means this is the eutectic product. Okay, if you apply in the binary diagram itself for this overall composition, the lever rule, then you will see that so and so amount of silver Ag3Sn phase will form, rest will be tin phase. So then next what happens is, the liquid stays at the eutectic composition, and that as it solidifies via the eutectic reaction. Okay, so the liquid is going to give three solids. That's the ternary eutectic point. Okay, so what happened to the solid composition now? It has come here. The solid also now is getting enriched in copper, because a copper rich phase is now added to the solid. The composition of the solid moves towards the bulk composition. When the solid reaches the bulk composition, the system is fully solid and the reaction is complete. Meaning, this is the overall composition now. It has now crossed the solidus. Okay, so below that, the entire thing is going to be solid. So the overall composition is now entirely solid, and the solid is going to have all these three phases. The Cu6SN5 is only appearing after the ternary eutectic reaction. So the paths of the solid green and the liquid blue during the cooling are shown and the arrows. So you can see here, this is how the solid composition changed, eventually reaching the overall composition. Liquid's composition started from the overall composition, started shifted with more, getting enriched in copper more and more. Finally, when the solidification is complete, whatever solid formed is going to add to this overall composition here. So that's why the solids composition moves along this line. This is how a liquidus projection is useful in identifying what happens during solidification of alloy. That's how informative liquidus projections can be. So they help us in understanding solidification behavior in processes, let's say like additive manufacturing, welding, casting, and so on. And they help in preparing something called as the reaction scheme. It's quite useful for modeling. We will see about that later. Thank you. I hope the lecture is useful. See you in the next class.